Hi, welcome. In this video, we will solve problem number of connected components in undirected graph asked by many companies like Amazon, Facebook, Apple, and Microsoft. Now let's solve one more problem on graphs. One very again good problem on graphs. Okay, if you are trying to give interviews on a basic mediocre level, like companies from 8 to 12 package, and if they are introducing graphs, they might ask these types of questions. These are basics, okay, but yes, these are from very advanced topics, that is graph. Okay, so these can become right, and sometimes in interviews where the interviews depend on too many discussions, these types of questions will come, right? Because graphs backtracking comes with a very good amount of discussions. Okay, so let's solve this problem. We have number of connected components in an undirected graph. So I hope first of all this is clear to you what is directed graph and undirected graph. Basically, if we have one as a node, let me clear you this up. Okay, and let me clear you here. Suppose this is one node. Okay, this is one node, and if I am writing like this is an undirected graph. Okay, like this is an undirected graph, because here you don't know the direction, right? Here you know that one is connected to two, okay, and you know that two is also connected to one. Okay, similarly here two is connected to three, and three is also connected to two. So this is known as undirected graph. Okay, now what are directed graphs? Okay, let's quickly check. Suppose I have one node here, one, okay, that is connected to two in a direction. Okay, now two is connected to three in a direction, right? 3 is connected to 4 with a direction, right? So here 1 is connected to 2 only, right? 1 is connected to 2, but 2 is connected to 3, right? From 3 is you can connect to 4. So basically what this mean is, right, when I'm saying 1 is connected to 2 is connected to 1, so suppose if you are doing a traversal, right? Okay, you know about traversal. Here we have DFS and BFS traversal. In graphs, these are the two methods to traverse. Okay, so from 1 you can reach to 2, right? And you can reach to 3 as well. From 2 you can reach to 1 as well, right? But here from 1 you can reach to 2 only. From 2 you can't reach to 1, right? Okay, you can't reach to 1, you can reach to 3 only. From 3 you can reach to 4 only. Okay, so this is the way here in mm, basically in directed graph. We say this is directed graph. Okay, and that's why you can see here the edges are also less. Here you will find two times of these edges, right? Basically here one edge is 1 to 2 and 2 to 1, but here we have only 1 to 2. Similarly here we have 2 to 3, 3 to 2, but here we have only 2 to 3. So this is the basic difference between undirected and directed graph. Basically how we can use undirected and directed graph by using DFS and BFS traversal. Okay, now let's come back to question. Okay, so there is an undirected graph with n nodes. So these are n nodes here. This is there is also an edge array. Okay, so these are basically edge arrays. Okay, where edge I is represents a by b, means that an edge between node A and B. So basically, if I'm writing 0, 1, that is means suppose this is one node that is 0, okay, and this is one node that is of 1, right? So this there is an edge between 0 and 1, right? Similarly, we have an edge between 0 and 2, so this is 0, okay, and this is 2, so we have an edge between 0 to 2. Okay, between node A and node B in the graph, the nodes are numbered from 0 to n minus 1. So if it is 3, it will go to 0, 0 node, 1 node, and 2 node. Okay, return the total number of connected components in that graph. Okay, so now let's understand what is the basic meaning of connected components. Okay, so see here, suppose this is one graph, right? I have this node 0 connected to 1, connected to 2, connected to 3. Okay, and this is connected to this one, right? Then I have one, Okay. So this is one graph basically, or you can say one graph component, right? So this is one graph component and these all are connected, right? I will say one graph component, right? This is second graph component, okay? This is third graph component and this is fourth graph component, okay? Here you can see these are not connected. This is itself it connected. This is itself connected. This is itself is connected. This is itself connected. So we need to tell what will be the number of graph components, right? What will be the number of graph components in an undirected graph. Okay, so this is undirected graph and these are the number of components. So this is what we need to tell. Okay, so now let's see sample input and output. Here you can see there is only one component, 0 to 1 and 0 to 2. So the answer will be output as 1. Okay, now here you can see when we have 0 to 1, okay, then we have 1 to 2, then we have 2 to 3. So let's suppose 2 to 3. Then we have 4 to 5, right? So 4 to 5, it's a different one. Okay. And that's why the output is 2. This is one graph component. This is second graph. Okay. So I hope you are clear with the problem statement, right? Now let's see how we are going to solve this problem, right? So basically, suppose this is a problem, right? We have different graph components. How we will figure out that how many graph components are there? Okay. So what is the method of traversal, right? That is either we can use DFS and BFS. Okay. So if I am applying DFS, I can traverse from here to here, right? And then from here, I can traverse in basically erase this one, right? I can traverse through entirely, right? Here to here, here, but I won't be able to traverse here, right? But itself here I can traverse, right? Itself here I can traverse. Okay. So how I will apply DFS to all, right? If I basically, how we basically do DFS, suppose if we have components like this is component 2, 1, 2, then we have 3, right? Then 4, then 5, okay, and 6. So basically it will, if we apply DFS here, it will go to and you find to all the nodes, right? But here what we will do? So basically what we will do, if you can see, we have given, okay, n is the number of nodes. Okay, so here we have how many nodes? Here we have 10 nodes, right? So what we will do, we will call each node, we will call DFS on each node one by one, right? And suppose if I am calling this, right, you can solve this problem either by DFS and BFS. Okay, no issues. So I am doing it by DFS. So if I am calling this by suppose here 0, right, it will go to 1, right? It will go to 2, it will go to 3, right? My single DFS call that is started from DFS 0, right? That is started from 0, it will go to 1, it will go to 2, it will go to 3, right? What I will do, once it is go to 1, 2, 3, I will mark as true, right? In my visited, okay, you can take some visited space, okay, or suppose my visited array, I will mark these nodes are as true, that here we have visited. So now when I will call DFS 1, right, it will say that you have already visited, no need to visit. Then I will call DFS 2, right, it will say you have already visited, no need to visit. Okay. Similarly, if I call DFS of 3, it will say you have already visited, no need to visit. When I will call DFS 4, that is not visited, right? That is not visited. So here what I will do, I will call this function. So what we will do, we will try to check when I am actually calling the function. Here I have called function, here I have called the function, right? Now after 4, this 4 will make all this node as true, this as not true. So if I call basically DFS 5, it will say you have already visited, no need to call this function, right? If I say DFS of 6, you have already visited. So when I will call DFS 7, right, it will say yes, this you can visit. So what I will do, I will simply calculate when my function is getting called, right? When my function is getting actually called, right? I will trace down it and that will be my number of, basically number of graph components. Clear? Clear with this approach, right? This is we are going to do. Okay. what will be the things that we will be requiring? If I'm applying DFS, right, I will be requiring one adjacency list or matrix. So I will use adjacency list here, right? So we use adjacency list and visited array. Okay. And by this, what I will do, I will simply find out the number of graph components. Let's do a quick demo of it, right? How we are going to proceed of it and how we are simply using adjacency list, visited array, everything. Okay. So let's try with one example. So now let's suppose we have this problem, right? Where we have one component, right? Second component and third component. Total three components, one component, second component, and third component, right? And we have provided with nodes. Number of nodes are 5, 1, 2, 3, 4, 5, 3, 4, 5, and 6. I guess there should be 6 nodes. Yes. So number of nodes are not 5. These are basically 6 nodes. And we have provided with the edges. You can see 0, 1, right? Then 1, 2, and then 3, 4, and 5. We have no edges. So let's see how we will solve this problem, right? So from this edges, right, by the help of edges, we will create an adjacency list. Okay, so let's create an adjacency list. So here is my adjacency list. Okay, you can see this is my adjacency list. Okay, now in this list, I have basically this will be a 2D array. So 0, 1, 2, 3, 4, 5. Right. So 0 is representing 0 node. Right. So 0 is connected to which node? That is only 1. So I will put 1. But how I will put it? That's true, right? How we are going to put it. So let's see. What I will do, right? I will simply traverse through edges, right? I will find 0 and 1, right? 0 is connected to 1. So what I will do, in the 0 index, I will put 1, and in the 1 index, I will put 0, right? Similarly, what I will do, I will come here, I will check 1 is connected to 2. So in the 1, I will put 2, right? And in the 2, I will put 1, like this one. Then I will check 3 connected to 4. So in the 3, I will put 4, and in the 4, I will put 3, right? So here you can see your adjacency list. It's like this one, 0, 2. Here we have only 1. Here we have only 1. And here we have 4. Here we have 3. That's basically a 2D array. Remember, 2D array. So what is happening here? You can see here we have 1. So 0 is connected to 1. That's true, right? This is 0th node, right? These you can understand by the nodes. So this is 0 node. 0 is connected to 1. Okay, done. 1 is connected to 0 and 2. Yes, 0 and 2. 2 is connected to 1. Yes, 2 is connected to 1 only. 3 is connected to 4. Yes, 4 is connected to 3. And 5 node is not connected to anyone. Okay, that's an empty. Okay, that's an empty. Okay, so what we will do, we have created an adjacency list. Now what we will do, we will create a visited array that will mark that if we have visited or not, right? So let's quickly create a visited array. So this will be my visited array, right? Here I have marked everything with false because that means I have not visited anyone. Okay, I'm marked with false. Now what I will do, I will simply use an iteration, right? And I will basically use an iteration, suppose a for, okay, that will start from 0 and it will go till the number of nodes, that is 6. Okay, so you can see till less than 6. So let me put it 5, till it will go till 5. Okay, because it's to call each node. Now here what I will do, I will call my DFS function. All right, I call my DFS function. So I will call first DFS 0, but I will only call when my visited is false, right? So if I say if not visited, that is not visited. Okay, suppose visited of I, not visited, that means if it is false, right? Then what I will do, I will call my DFS of I, right? So basically here I will start from 0, right? Then it will go to 1, then 2, then 3, then 4, then 5. Okay. Let's see when I have called DFS 0, right? It will go to DFS 0, it visited it, right? So what I will do, I will make this false to true. Okay. Let's use red pen. So I will make this to true. Then after this, I will visit 1 because, right, I will find out its adjacency nodes, right, adjacent node. So 0 is connected to 1. How I will get to know that 0 is connected to 1? By through adjacency list, right? I get to know that 0 is connected to 1. So what I will do, I will visit 1, right? So I have visited 1. I will mark this as also as true, right? So I will mark this as a true, right? Now, when I have at 1, I will find what are the connected of nodes 0 and 2. So 0, I will check 0, I have already visited, right? So I won't visit. Then I will check 2, 2 is not visited. So let me put the indexes here as well. 2 I have not visited, so I will visit 2, right? And I will simply mark this as true, right? Now I have visited this one, okay? Now what I will do, I have done this one 0, 1, 2, okay? Now I will want call 3, right? So you can see here, right? I will basically count here. Whenever I am calling my DFS function, I will count here. So you can see when I have called, right, 0, it counted, right? Count is equals to 1. Count is equals to 1 when I counted it, okay? Now when it was 1, the visited array was already true, so I have not called it. When it count to 2, the visited array was already true, I have not called this DFS function, right? So see, it will call only when visited it's false. So here you can see visited 3 is false. So now it will call it, right? So it will call it and count will update it, right? And if I'm calling it, what I will do, I will visit this one and I will check what is adjacency of 3, that is 4. So I will visit this one, right? So what I will do, I will mark this and this as true. So I will mark this one as true. I will mark this one as true, right? Once I have done this one, right, I will come back and I will return, right? So count is updated to 2. So now you can see, now I don't need to visit 4. So if I make you clear that here we have visited 0, I have called 0 and 1, 2 was not called by DFS function. Similarly, I called 3, 4 was not called by DFS function. Now I will come to 5 and I will call this one, right? So I will come to 5, right? I will check 5, there is no adjacency. So I will simply stop and I will mark this as also as visited. So I will mark this as a true. Now once I will come back, right, all the nodes are visited, right? And the count will be updated to 3 because I have called my DFS function only 3 times. Okay. So this is how we are going to solve this problem. And I hope you are clear with this approach. What we need to do, simple, right? We need to use a for loop, any loop, use basically an iteration. You will start from 0 to 5, right? And you will call DFS function. Now you will call DFS function only when the visited array, it's not visited, right? If that node is not visited. So you can see 0th node not visited, you called it. Now by this DFS alone, it visited to all its connected nodes, right? So it visited the connected nodes. Once this is done, it marked all the nodes as true, right? After this, you visited the third, you called the DFS 3, you visited. So this is how you will count it. Okay. So yes, I hope you are clear with this approach. In the next video, I will give you a quick code implementation, how we can do the code, okay, how we can simply solve it by code. And before that, if you want, we can go with the pseudo code as well. Okay, let me write a pseudo code for it. So that you will get a bit of idea basically how I'm proceeding it. Right. So what I will do, I will first create a visited array. Okay, you can create a visited array of n size. Okay, again, it's a pseudo code. And then I create an adjacency list, right? Now, how you need to connect, basically create an adjacency list. Basically, what you do, you will simply find out u and v from the edges, right? So you will find the u and v of edges. So let me say, suppose let u comma v of edges, right? And what you will do, you will push, right? So you will say adjacency of u dot push v and adjacency of v dot push u. Remember how we created basically. So this will create an adjacency list. Now after this, what you will do, you will take one variable that is count, that is starting from 0, and now you will simply call your DFS function. So you will simply start a loop that will start 0 to n number of nodes, right? And you will check if your particular node it's not visited of I, you will simply, what you will do, you will call DFS function. So you will call DFS function with I, you can pass your visited array and you can pass the adjacency list, right? So you will pass DFS here I and visited array adjacency list. After this, what you will do, you will update the count plus piece. Now, how my DFS function will look like? It's again very simple, right? So this is my DFS function with I with visited array, the adjacency list. So what I will do, I will basically say when I will call this function, I will first do visited I equals to true. That means I have visited it. Okay. Now what I will do, I will simply find out the adjacency list. How I will get adjacency list? I will say find the array that will be adjacency of I, that is node, right? So I will get the array. Remember, I will get this array, this as an array, right? Once I have get this as an array, what I will do, I will start traversing here. So I will simply start from j, suppose j equals to 0 to adjacency length, right? And what I will do, again same thing, if I have not visited the particular array of j, right? Simply visit DFS of array j with again the same visited and the adjacency. Okay, right? So I will visit with the adjacency list, right? But here, how we will get the adjacency list? So the same adjacency list that you have created, right? You can pass it. Even if you not pass visited and adjacency, still you will get the answer, but it's better to pass because again, remember the state references. In recursion, we need the state references, right? So it will get the state reference. Okay. So basically, this is how you can code it out. Now, suppose you need to find the number of components, right? So basically, I want this is one component. So I want 0, 1, comma 2, right? I want 3, comma 4. Okay. I want 5. I want these number of components separately alone, like this one, 0, 1, 2, 1. So that is too possible, right? You can create one, suppose a res array. Okay. And whenever you are calling DFS function, right here, you are calling DFS function, what you can do, you can simply say res, suppose you have visited one, you will simply say res dot push. Okay. Basically you will push I here, that means it will come to your resultant array. Once you have pushed it, what you will do, you will, after this count, you will, suppose you will take answer array, because you will get the answers and you will say answer dot push, and here you will simply push the rest elements, right? So triple dot rest, because if you simply push rest will be basically gets empty because it's recursion call. So to push rest as well here, and that's simply an answer. You will simply push rest, once it will come back. Now here just you need to pass one variable more, that is rest. Okay. So here, this is basically adjacency. Here you will pass your res resultant here, here, and here. Okay. So whenever you are getting, you are simply pushing it, right? It will come to here. Before that, you can simply say your res is basically it's 0, it's empty. Okay. That's a simple storing method. You can simply say that currently your S is empty. Okay. Once you are passing it, you are passing all, you are simply pushing all the elements, right? You will come to it, you will simply put in the answer and your answer will hit the number of components. Okay. So yeah, this is how you can solve this problem. Okay. I hope you are clear with it. Now let's discuss the time and space complexity of this approach. So now let's first discuss the space complexity of it. Okay. So here you can see, right, we have taken one visited array, one adjacency list, right? So this visited array, right, will be having big O of n space, adjacency list, because I will store all, it will be like a 2D array. So in 0 can have 1, then each one have can 2 elements, right? So I am considering this will be 2 node, plus for the recursion stack that will go till n, assuming that you have only one component, right? 1, then 2, then 3, right? So it will go till number of nodes your function DFS call. Okay. So basically this is for visited This is for adjacency list and this is for the recursion stack. Okay. So again, right, adjacency list in most of the problems you will get got this adjacency list, but here it is not, right? So you can consider this big O of 2n, right? But the overall time complexity will be big O of n in if I am not considering adjacency list. Otherwise, the time complexity will be big O of n plus big O of 2n plus big O of n. You can say it's big O of 4n, right? But overall, if adjacency is not given and we are coming with this one, so it will be big of n. Okay, now let's talk about the time complexity. What will be the time complexity? So first of all, let me clear you few of the things for the undirected graph. Okay, for the undirected graph, the time complexity is v plus 2e, and for the directed graph, the time complexity is v plus e. Basically, how this comes, so in why it is 2e, because you can see in directed graph, right, there is no direction. So if I'm calling dfs 1, it will go to its neighbor 2, right? If I'm calling 2, right, it will also go to its neighbor, right? So here you can see for each one I'm getting 2 calls, right? Now for here, okay, when we have 1 that is connected to 2, right? So what is the connection of with 1, right? So that is connected to 2. So if I am calling dfs 1, it will go to 2, but 2 won't come to here, right? So we have only single edge, right? Here 1 is connected to 2 and 2 is also connected to 1. So on each function call I am considering 2 as a neighbors, right? Each node will have approximately 2 as a neighbor. If I created, like here you can see this is an undirected graph, 2 has 2 neighbors, right? Suppose if I'm created this one also, each node will have 2 neighbors at worst. Okay, here each node, right, in the directed, each node will have 1 as a neighbor. That's why it is v plus e, it's v plus 2, right? Now this is for the traversal, right? So if I'm applying dfs here, right, or vfs, this will be the time complexity, right? Similarly here. Okay. Now you are basically calling DFS in a loop. So if you can see here, right, you are 0 to n, you are moving here and you are calling this DFS function. Now DFS working this internally, right? So this time complexity will be v plus 2e, right? But why it is not 2e, why I will change it to v plus e. Okay. Why? Let me clear you first. See, you are using visited array. Okay, that means each node you are visiting once. Okay, so once I have called 0 to 1, right, and if I am calling 1, you won't visit 0 because that is already visited. So by the help of visited array, you are now simply traversing each node only once. So with big of v, number of nodes plus edges. Okay, now this is n times DFS call. So you might can say big of n into v plus e, that is n into v plus e. That is, I will say again, still it will be wrong. Why? Because on each node you are not calling dfs. You can see dfs will call at I equals to 0, and like here it called at I equals to 0, I equals to 3, and I equals to 5. Okay, only 3 times. Okay, my dfs function call, right? So I will say that let's see the broader perspective, right? Here you are visiting each node, you are visiting each. So no matter you are visiting each node, that is only 5, right? So if you can take, right, this ith loop that will run for n times, but you are not calling the dfs function in each time, right? So it will be big of n plus v plus e. That is your DFS time complexity. So the total overall time complexity will be big of n plus big of v plus e. Why v plus e? Because we have used the visited array by which we are not visiting the 2 neighbors of each node, right? And this is also overload will be comed as big of n only. Why? Because if you see the overall perspective here, you are visiting each node only once. Okay, you are not visiting each node and you are not calling more than that of it. Okay, so that is again overall will be big of n. Thinking of suppose each node is once, right? Suppose each node is like this 1, 2, 3, 4, 5. So there will be only that call, right? So the time complexity here big of n, here space complexity is big of n, and that's yes, the problem is done. Okay, we are good to go ahead with the code implementation. Okay, so in the next video, I will give you a code implementation of this problem. Okay, we will check the how we can apply the code, and then in the next video, I will talk about the dry run. Okay, so that's all for this problem. See you in the next video.